Everything we've been doing up until now with center of mass and Newton's second law for a system of particles has prepared us to discuss something called the linear momentum. And momentum is very closely related to Newton's second law and forces in general, which is why we spent a lot of time discussing those concepts before jumping straight into this. So let's just go ahead and give ourselves a definition for the linear momentum. So the linear momentum is a vector quantity p that is equal to the mass of the particle times the velocity vector v. So this is our linear momentum for a particle. And since m is a scalar, as we know that momentum and velocity have the same direction. And then from this equation, we can also derive the SI unit for momentum as kilograms times meters per second. And momentum, as I said before, is very closely related to force because Newton can express his second law of motion in terms of momentum, which relates the time rate of change of momentum of a particle. So time rate of change, we know that time rate of change is equal to dp over dt. So this is our rate of change of momentum with respect to time. And this is equal to the net force acting on the particle. So this is simply equal to F net. This gives us a very neat relationship between the net force and the linear momentum, which tells us that the net external force on a particle changes the particle's linear momentum. And this also tells us that linear momentum can be changed only by a net force. So if there is no external net force, if F net is equal to 0, then dp over dt is also equal to 0, meaning that the linear momentum cannot change. And if we manipulate the right side of the equation, we get dp over dt equals F net, which equals d over dt times mv, right? Because we know bring in this equation, that's how we get that equation. So let's move to the bottom because we need more space. So we get F net equals d over dt times mv. And since m is constant, it's not changing, we can rewrite this as dv over dt. And we know that this is just equal to ma. So that is how we get the relationship between net force and linear momentum. And these are just equivalent expressions of the second law for a motion's particle. So this is what we get for a singular particle. But what if we have a system of particles? So what if we have more than one particle? So we can extend our definition of linear momentum to a system of particles. So let's consider n particles, just any arbitrary number n particles with its own mass, velocity, and thus its own linear momentum. So external forces may act on them. So the system as a whole will have a total linear momentum big P. And big P is just the vector sum of the individual particles' linear momenta, which is equal to P1 plus P2 plus P3 all the way until Pn, where n is our number of particles. And we can rewrite this as m1 v1 plus m2 v2 plus all the way until mn vn, since they, by definition, all have their own masses and velocities. So if we compare the equation with the one we got before, we can see that big P simply equals big M times the velocity of the center of mass. And that is why we discussed the center of mass before discussing linear momentum. So the linear of momentum of a system of particles is just equal to the product of the total mass of the system and the velocity of the center of mass. So let's take the time derivative of this. We get that d of big P over dt is equal to m dv center of mass over dt, which is just equal to m times the acceleration of the center of mass. And if you have watched the last video, we talked about Newton's law for a system of particles. And this is the exact same equation that we got in that video. And if you haven't watched that video yet, I recommend you go back and review it because it is very helpful when working with system of particles and forces. So this just tells us that F net is equal to d of big P over d of t. And this is the generalization of the single particle equation to a system of many particles. So this tells us that the net external force F net over here on a system of particles changes the linear momentum P of the system. And the linear momentum can be changed only by a net external force. Similarly to a single particle, if there's no net external force, then the total linear momentum of the system of particles cannot change because dp over dt would equal 0. So overall, this gives us a very extremely powerful tool to solve problems. And I hope you guys have learned something new. Come back and join us in the next couple of videos where we'll actually be solving some problems.